Welcome back to the video lecture series on the course Engineering Mechanics. Today we will discuss the topic equilibrium of forces. In this presentation, we are going to learn equilibrium of forces and equations of equilibrium and the conditions of equilibrium. Let us start equilibrium of forces. Let us consider a body which is acted upon by a force P like this as shown in figure. Now, the body cannot be under equilibrium by the action of a single force because the force P is tending to move the body in its line of action. That means we must require at least one more force which can balance the applied force. If you have applied another force in the opposite direction and equal to the force which is already applied, then the forces will balance themselves. Now, the one force is acting towards right and the another force is acting towards left. Both are equal, right? Similarly, now a force Q is acting in the vertical direction downward. Now, the body is not said to be under static equilibrium because there is an unbalanced force in the vertically downward direction. Even though horizontally the forces are balancing themselves, vertically the force is not balanced. If you introduce another force in the vertical direction upward and equal to the existing force, then now horizontally the forces are balanced and vertically the forces are balanced. This condition of the body is said to be static equilibrium. Equilibrium of a body is a state in which all the forces acting on the body are balanced by themselves and the net force acting on the body is zero. Here, even though four forces acting on the body, the net force acting on the body is zero. That's why this body is said to be under static equilibrium. In other words, when the resultant of the system of forces acting on the body is zero, then the body is said to be under equilibrium. If the resultant is zero, that means the net effect of number of forces acting on the body is zero. Resultant is nothing but a single force which is replacing number of forces acting on the body without changing the effect. So, a resultant is representing the number of forces acting on the body. It is nothing but the final net effect of system of forces. If that final net force is zero, that means resultant is zero, the body is said to be under equilibrium, right? Now, when the resultant becomes zero, what is the equation for resultant? If number of forces acting on the body, we will resolve the forces into horizontal components and vertical components. Finally, the equation for resultant is sigma h square, algebraic sum of all horizontal components sigma h and algebraic sum of all vertical components sigma v. If this equation is satisfied or resultant is zero, then only the body is said to be under static equilibrium. When this equation will be satisfied? The equation will be satisfied only when both sigma h and sigma v are zero. If sigma h is 0 and sigma v has some value, that means vertically the forces are not balanced, then you will get a resultant. We will get a value for the resultant. We will get a value for the resultant means the forces are not balanced and there is an unbalanced force acting in that direction. Now, if these two equations sigma h and sigma v is 0, that means the algebraic sum of the forces acting in horizontal direction, the algebraic sum of the forces acting in vertical direction is 0, then the resultant becomes 0. Now look at another example. In this example, two forces acting at some distance parallel to one another. Both are equal and opposite. Now let us put the definition to this case. Here sigma h is 0. Sum of all horizontal components is 0 because there is no horizontal force at all. So sum is 0. Now look at sigma v, sum of all vertical components. Look at. So I am assuming upward positive and downward negative. So here the sum of all vertical components is plus p minus p is equal to 0. Here sigma h is 0 and sigma v is also 0. That means both the equations are satisfied. Here the resultant of forces is 0. Still the body is not under static equilibrium condition because the body is under the action of a couple. Here these two forces P and P, which are parallel equal, forming a couple. Two equal unlike parallel forces forms a couple. So it is under the tendency of rotation in clockwise direction. So we cannot say the body is under static equilibrium unless the couple or moments are also balanced. That's why we are introducing one more word into our previous definition of equilibrium. Now the equilibrium of a body is the state of the body in which all the forces acting on the body are balanced by themselves and the net force acting on the body and the net moment due to the forces acting on the body is also 0. We are introducing the net moment also because even though the forces which are acting in horizontal and vertical direction are balanced, if at all any movements are there, unbalanced movements are there, that will tend the body to rotate either clockwise or anti-clockwise. So we need to balance that also. In the first case, it is the body is under static equilibrium because the moments are also 0. All the forces meeting at same point and they are not producing any movement about the center of the body. But here there is a couple which is in the clockwise direction. So the second case is not a case of static equilibrium. So here the equations of equilibrium are sigma h equal to 0, sigma v equal to 0 and sigma m is equal to 0. Sum of all horizontal components of the forces must be 0. Sum of all vertical components of the forces must be 0 and also sum of all moments about a point is also equal to 0. Then only the body should be under static equilibrium condition. Now look at the equations. The equations of static equilibrium. Sum of all forces acting on the body is 0. That means sum of all forces or algebraic sum of all forces is 0. It is not that no force is acting on the body. Even though 100 forces acting on the body, the algebraic sum of all 100 forces must be 0. Look at this. Sum of all forces acting along x direction is equal to 0. So this is one equation of static equilibrium. So horizontally, this is positive side of x and this is negative side of x. I am assuming like this. Now whatever forces acting towards right side or positive side must be equal to the negative side. Then the forces or net force or algebraic sum of the forces must be 0. It will become 0. Similarly, sum of all forces acting along y direction is equal to 0. Look at this. Now I am assuming upward plus and downward minus. The sum of all upward forces must be equal to sum of all downward forces. So that what happens, they will balance themselves and vertically there will be no unbalanced force. And similarly, finally, sigma fz equal to 0. Sum of all forces acting along z direction must be 0. See here, this I am assuming negative side and this side I am assuming positive. Whatever the forces acting along the positive side of z-axis must be equal to negative side of z-axis so that there will be no unbalanced force along z-axis. These three are static equilibrium equations along with moments. We have one more, three more equations that is related to moments. Now, moments about xy plane, yz plane and zx plane must be 0. Here, fx, fy, fz are arresting or balancing the translatory motion or translatory effect on the body. Now, look at the moments. Moment about xy plane is 0. Moment about xy plane must be 0. See, the moment about xy plane must be 0, and moments about yz plane must be 0, and moments about zx or xz must be 0, right? So, these 6 equations are called equations of equilibrium when the body is acted upon by forces or moments in all the 3 mutually perpendicular directions. Now, consider for a plane case. If it is a plane problem, there will be only x-axis and y-axis, and there will not be any z-axis. For a coplanar system of forces, there is no z-axis. All forces are acting in one plane, that is x and y plane, xy plane only. Now, look at the equations. The equations will reduce to a number 3. For a plane problem, sigma f equals 0. That means sum of all forces acting along x direction equals 0. Generally, we will write it as sigma h equal to 0. Sum of all horizontal components equals 0. And then sigma y is also equal to 0. Sigma x is 0 and sigma y is 0, and we will take only one moment, that is moment about a point. Moment about a point in the xy plane. So, there are only 3 equations for static equilibrium for a coplanar system of forces or plane problem. So, sigma x equals 0, sigma y equals 0. Generally, we will write this equation as sigma v equal to 0. Sum of moments about a point in the plane must be 0. These 3 equations are equations of equilibrium for a plane problem. Now, look at the conditions of equilibrium. See, when 2 forces acting on the body, when the body should be under equilibrium by the action of these 2 forces. Only 2 forces acting on the body. What is the condition for equilibrium when 2 forces acting on the body? Let us look at this. When 2 forces acting on the body, they must be equal, opposite and collinear. Then only the body is said to be under static equilibrium. If a body is acted upon by 2 forces, they must be equal, opposite and collinear. They must act along the same line. Then only the body will be said to be under static equilibrium. If the forces are not collinear, then what happens? Look at this. If the forces are not collinear, even though sigma h is 0 and sigma v is 0, right? So, here sum of these 2 forces, algebraic sum of these 2 forces is 0, because this is plus p and this is minus p. Even though sigma h and sigma v are 0, the body is under the tendency of an unbalanced clockwise couple of intensity P into D, where D is the distance between the 2 parallel forces. P into D is the couple. The body is under the tendency of clockwise rotation. So, this is not under static equilibrium. This is under the tendency of rotation, right? Now, how to bring this system into equilibrium? So, there must be an opposite couple to balance the actual couple P into D. Then only the body will come back to equilibrium here. That means we can take 2 forces. We can take 2 forces which is equal to 2P and 2P. Again, 2 parallel forces. The distance between these 2 is D by 2. distance between the two parallel forces is d by 2, and these two forces forming another couple which is equal to 2p into d by 2 pd. And what is the nature of this couple? This couple is in anti-clockwise direction. Here the couple is clockwise, and now we have introduced one more couple, that is anti-clockwise of same intensity. Now sum of all horizontal forces 0, sum of all vertical forces 0, and sum of all moments is equal to 0 about a point. Moments about a point is equal to 0. Now the system is said to be under equilibrium. A single force cannot keep the body under equilibrium. A couple cannot keep the body under equilibrium. When a single force is acting, we must require same, equal, opposite, collinear force to bring the system into equilibrium. When a single couple is acting, we require equal, opposite couple to bring the system or body to static equilibrium. Now, when three forces acting on the body, what is the condition? When three forces acting on the body, look at the diagram. Now, if three forces F1, F2, F3 are acting on the body simultaneously. Now, the condition for equilibrium is the resultant of any two forces must be equal, opposite and collinear to the third force. You take any two forces, say F1, F2 in this example. I'll take F1, F2 and I'll find the resultant of these two forces. The resultant of these two forces, if you find the resultant of F1 and F2, it must be equal, opposite and collinear to the third force. The resultant is equal to F3 and it is in the opposite direction and it is in the same line of F3. Then only the body will be said to be under equilibrium. If four forces acting on the body, now tell me what is the condition for equilibrium. If four forces acting on the body, we can say the condition is the resultant of any two forces must be equal, opposite and collinear to the resultant of other two forces. Or we can say the resultant of any three forces must be equal, opposite and collinear to the other force. Like that we can write the condition. If more number of forces acting on the body, more than two forces acting on the body, we will reduce the system to only two forces and we will apply this condition, the same condition, equal, opposite and collinear to the system. Now, in this video, we have learnt the static equilibrium and we have seen the equations of equilibrium when it is a spatial problem or a three-dimensional problem, and we reduce the equations to a plane problem or 2D problem, that is XY plane only, and we have seen the conditions of equilibrium also. Thank you.